Hey, good afternoon, well actually good morning, and welcome to another exciting episode here of Advanced Level Chemistry at Spain Park. Today is Friday, September the 20th. September is zooming by. It is homecoming here at Spain Park. And if you are enjoying these exciting Advanced Level Chemistry videos, please feel free to hit that like button and smash that subscribe button. Hey, we're up to like 160 subscribers now. We got to hit that 200. Pretty soon I'll start making like a penny for every 10 videos. Who knows? So anyway, yesterday we've been talking about the three different states of matter, but we learned that really there's more than three. There are how many? 5 different states of matter. Okay, with the plasma being at what conditions? When is a plasma made? Super high energy, okay? And then the 5th one was really cold, and it's called
Something Einstein.
Something Einstein. You remember his name? The Bose-Einstein condensate. Okay? So when we look at these, everybody just saw my nail. Okay? Oh, I got to get to the right.
Yeah, you can maybe blur that out with those.
Yeah, well, that's not going to happen. I don't do any post-video editing. We're going to go here, and we're going to go to here. Yeah. Well,
I don't know how to edit. I figure it out though.
yeah. I mean, I can figure it out, but it already takes forever to upload these. So, it's just, hey, only 3 people are watching them anyway, so it really isn't that big of a deal. So we were talking, all right, let's refocus. Now get your notes out. Everybody have your notes out. And yesterday, again, we were talking about the phases of matter. And I will make this PowerPoint available to you at some point, probably next week. Okay? But when we look at this, we talked about the differences between a solid, a liquid, and we have all the properties then of a solid, a liquid, and a gas. Okay? We remember that, okay, without getting your notes out too much, what's a vapor?
Something that's normally a solid or a gas or a liquid at room temperature.
Normally a solid or a liquid at room temperature. Okay? So that's everything we talked about. And then here we just have a plasma and a Bose-Einstein condensate. So those are the things we talked about yesterday. Now, today we're going to start talking about matter, the classifications of matter. Okay? So we're going to be looking at matter and how it can be classified. But the first thing is what do you think matter is? What do you think matter is? Come on, y'all. You learned this in 5th grade.
How much space something takes up?
No, that's volume.
Or mass.
Okay?
How much stuff is inside? That's mass.
That's mass.
Anything
Okay, so hold on. Here we go. I think we have an answer.
that takes.
Okay, anything that takes up space and that's volume. Anything that takes up space, it doesn't just have to have volume, it has to also have what's density a ratio of? Mass and volume. Anything, matter is anything that has volume and mass. Now that's going to include atoms, elements, molecules, compounds, all of that. This is all just going to be matter. This isn't in your notes. We just defining matter. This is something that I'm assuming that we already know, which maybe was a false assumption based upon the length of time it took to get the definition. Okay? But it's just stuff. It's just anything that has mass and occupies space. Anything in the universe is either matter or is energy. And we're going to kind of differentiate between both. So if we look then at matter, anything that has mass and occupies space, matter is going to be, this is going to be the flow chart that we're going to use for the rest of the year. Okay, so far we've pretty much just been talking about measurements and systems and significant figures and all of that. But now we're going to get into, okay, what is the composition of matter? What are the changes that the matter undergoes? That's what chemistry is. So matter is either going to be a pure substance or it's going to be a mixture of substances. Okay? Now, a pure substance is either going to be an element or a compound, and a mixture is going to either be homogeneous or heterogeneous. If it's homogeneous, we're going to call it a solution. If it's heterogeneous, we're going to call it a suspension. Now, in this unit, this chapter, I'm going to introduce those three things on a very superficial level. Okay? We're just going to kind of go through and talk about different properties and things. And by the way, you need to know, Monday we're doing a lab. Okay? Monday we're doing a lab. So maybe take your phones out right now and put a reminder in your notes that you need to wear long pants, closed-toe shoes. Okay? Make it a reminder for Sunday night and put the clothes out, and make it another reminder for Monday morning whenever you get up and get dressed, so you're dressed appropriately. Okay? Because we're going to be in this lab, we're going to have fire. We're going to be dealing with acids, dealing with bases, mixing chemicals together. Okay? So you need to have the appropriate lab clothes on for sure. So everybody make a alarm, one for sure you're not going to miss. Has everybody got it done? Okay, the girls, you guys saying, I know, I always wear long pants and closed-toe shoe anyway, so we're good.
Just in case.
Okay? All right? So come on, guys. Come through for me. We can do it. So we're going to do a lab on Monday, but we're just going to kind of introduce the very superficial. Then we're going to jump to chapter 3, and that's where we're going to start looking at an element. What's the smallest part of an element? An atom. So we're going to look at the composition of an atom. What do we know an atom is made up of? Protons, neutrons, and electrons. Okay? Where are the protons and neutrons located? In the nucleus, with the electrons going around it. And we're going to just learn the basic structures, a little bit of the history, how all the different parts were discovered. Okay? We're going to then look at how do we know how many protons, neutrons, and electrons everything has in it. Just kind of break the atom down. Then we're going to take a quantum leap to chapter 20, 21, to where we do radioactivity, nuclear chemistry. We're going to find out what makes the nucleus, some stable, some unstable. What makes them radioactive? What is radioactivity? Okay? And why is it bad? How can we use it positively for power? How do we make a bomb? How big is the boom of a bomb? I actually had the opportunity to speak with somebody on Tuesday that lives in Tokyo, in Japan. And so I was asking them about the ramifications of the bomb even this many years later, and we'll have a discussion about that. So we'll figure out what makes a nucleus stable or unstable, radioactivity. Then we'll jump back to chapter 4 and look at the electron class. How are electrons in these rings that you learned about in 8th grade or wherever? Are they really in those rings or their orbits? You know, all about the electron cloud. It's all very theoretical. It's going to be deep. Then we'll jump into the periodic table of the elements. All of the elements are on the periodic table. How is it arranged? What is the method to the madness there? And you'll be drop the mic type thing when we get to that part. Okay? Like, this is crazy. Ladies, focus. So then, once we get through all of that in chapter 5, then we're going to go to chapter 6 and start talking about bringing atoms together and making ionic bonds, covalent bonds. We're going to learn that there's going to be metallic bonds. What is it about the way they bond that gives the substances the properties? Have you ever wondered, how can hydrogen, that's a gas, and oxygen, that's a gas, come together to make water that's a liquid at room temperature? How can two gases make a liquid? It's one of the great mysteries in life. But you're going to know the answer. And then we're going to start naming those compounds in chapter 7. Chapter 8, then we're going to start doing chemical reactions, and that's when we kind of figure out how all that happened up there. Okay? Then we get into gas laws. How do gases themselves, what are properties of gases? And that's going to lead us then into a discussion of mixtures. And in mixtures, we'll talk about solutions in general, and then we'll end the year talking specifically about acids and bases, what makes those unique, and all that. So we're going to go through the whole year of just kind of talking about these things, breaking down matter. What's it composed of? Why is oxygen a gas? Why is water a liquid? And why is gold a solid? We want to know those things. Why is salt a solid? Okay? Why is salt NaCl? It's got sodium in it. Why can we eat that? But yet if you take sodium metal that it's made from, you put it in water, it blows up. Ooh. Inquiring minds want to know these things. I know you do. I know I just whet your appetite. Man, I can't wait for this whole year. Okay, so let's just kind of start with the first things, and let's just kind of talk about each of the three categories in general. And the first one is a mixture. Okay, now this is where your notes kind of start. And mixtures can either be homogeneous or heterogeneous. What does it mean to be homogeneous? The same throughout. Okay, so if I look at this right here, it's blue, it's got color, but notice it's clear. You can see through it. All solutions are clear. If it's a homogeneous solution, it's going to be single phase, one phase. You're not going to see parts with different properties. Single phase. Not necessarily colorless, but it's going to be single phase. It's going to be even throughout. Okay? It's called a solution. Solutions are your homogeneous mixture. If it's heterogeneous, it's going to be uneven throughout. Okay? I'm giving away the answer right here, but you ever wonder why don't the colors, why doesn't this separate? Why doesn't, when you have Gatorade, why doesn't the blue ever just settle to the bottom? In 1820, he was either English or Scottish. He was over there in that Great Britain area. A scientist named Robert Brown did a very non-exciting, he made an observation. He took some pollen grains, and those of you that have allergies, you know all about pollen. Okay, you can't see it really unless it's really bad. Like in the springtime, you can see the yellow just everywhere on your cars and on your back patio and everywhere. Okay, but he took some pollen grains, very tiny, and set them on some water in a petri dish and looked at it underneath a microscope. And he found that those pollen grains, no matter how still he got everything, the pollen grains just danced on the surface, just kind of jiggled about. And he was just kind of curious. He couldn't really understand why that did that. In 1820, he published his paper, but nobody was really too excited about it. Who cares about pollen grains jiggling about on the surface of the water? Okay? But in 1905, Albert Einstein was investigating the existence of atoms. Do atoms really exist? They knew matter was there. We're going to learn about the history, but he read that paper and he was able to explain the reason why the pollen grains were jiggling about was because of a thing now which is now known as Brownian motion, is that these molecules, and we know that if I look at a molecule of water, a beaker of water, the molecules in here heat them up, speed them up, cool them down, slow them down, right? So are they staying still inside of here? No. They're moving. We've learned now that they're moving rapidly. And so the solute particles of a solution are so small that the water molecules just keep buffeting them and keep everything all stirred up, so they never settle out because of that Brownian motion, that continuous rapid motion of the molecules of water, the solvent. Since the solute particles, and by the way, I'm making an assumption. Do we know the difference between the solute and solvent? Solute, if I put sugar into water, sugar is the solute, water is the solvent. Okay, we know that? I don't really need to define that, right? So the solute particles, the sodium and the chlorine, and when you dissolve salt, the water just buffets it and keeps it all stirred up so it'll never settle out. So this blue is going to stay blue forever and ever, amen. Because the water is just going to continually jiggle. It keeps it going. That's why its solutions never settle out. Even though there's gravity, the particles are just buffeted and stay in solution. Whereas heterogeneous, sometimes the particles get bigger and they do settle out, and we're going to look at that. Okay, so let's look at some examples of these. Okay? We have three types of mixture: small, medium, and large. A solution is the smallest solute particle. It's going to be atoms or molecules. It cannot be filtered. So if I take a piece of filter paper right here, okay, and we're going to need to know how to do this for tomorrow. Now watch. I need to make this filter paper, and we're going to do this on Monday in class, in the lab. I need to take this filter paper and put it into this funnel. You don't just cram it. Now look, I got short sleeves on, okay? But the hand is sometimes quicker than the eye. You ready? You take the filter paper, you fold it in half. Now I have a semicircle. Okay, you with me so far? Okay, now I take the semicircle and I fold it in half again. Now I have a quadrant. I have a fourth of a circle. Okay, now I have 1, 2, 3, 4 pieces of paper. If I grab 3 of them and squeeze, voila, it now fits perfectly into here. Now here's another little trick. It wants to pop out. Water is very sticky. So if I go and I put some water, just get it wet, now it's gonna stick. Okay? Ooh. That's worth coming to school just for today, just to see that, okay? Now, we take that. If I take this blue solution, the solute particles, this is copper sulfate, but it's dissolved as little tiny atoms and ions. I put this through here, clear out anything in there so we don't have any distractions. Okay, I'll probably slip and fall now back behind the counter because I got wet. What do we think? Blue or clear coming through?
Blue.
Okay, and you can probably already see what color is it coming through.
Blue.
Okay, so how does a filter work? I know, but how?
It
Has
catches
little
like
holes in
bigger particles and.
How's the water able to get through?
Has little holes in it.
Say that again.
It has little holes in
It
it.
has little holes in it. But if the particles are littler than the holes, what does that mean?
It's not gonna look up through.
It's going to go through. It's not going to filter, right? So since the blue is going through the little tiny holes, what does that mean about the stuff that's making it blue? It's small. Solution, the smallest solute particles, they cannot be filtered out by filter paper or by, it says a cell membrane, but the reality is we call it a semi-permeable membrane. Ooh, that's bringing you back to biology terms. What is a semi-permeable membrane?
Like some can get through and some can't.
Okay, say that again.
Some can get through and some can't.
And what's it dependent upon? The size. It's an even finer filter than filter paper. They have all different levels of filter paper as far as the size, but the semi-permeable membrane is the tiniest of tiny holes, only some things, but even the solute particles are small enough in a solution they can get through a semi-permeable membrane. Salt can get in and out of a semi-permeable membrane. Okay? Your cells have salt on the inside. Alright? They don't sell out due to gravity. And if you want to put right kind of here, that's due to that Brownian motion. They don't sell out due to gravity because of that Brownian motion. And lastly, they do not give the Tyndall effect. Now I'm going to hold off on that one until we talk about this, okay? I'm going to show you this Tyndall effect. But we can all see right now, right, that the filter paper is not filtering out the solute out of this. So I'm going to just save this. We don't need to just keep going on. Okay? But now we go to the next one. Yes, small, medium, and large. It's kind of Goldilocks things, you know. You don't need to video me washing our dishes. Okay? Now I have another solution right here that's a starch solution. This is a colloid. It looks just like a normal solution. Okay? It looks homogeneous. Now, colloids are the medium size, and they're kind of if it's on the small size of a colloid, it's going to be homogeneous. If it's on the bigger size of a colloid, sometimes they look more heterogeneous. They're kind of that intermediate. Okay? But when I look at this, this is not going to sell out due to gravity. It's not going to be. I can't filter it, and I'll try to filter this one in a second. But it gives this thing called the Tyndall effect. And the Tyndall effect is, okay, so I have a pointer here, okay, so everybody kind of sees the pointer going around. We turn the lights off. If I shine, well, let me just even take a solution first. This is a solution of salt water, okay? And if I put my pointer through that, can you see the beam going through the water at all? Through the salt solution at all?
No.
Even if I take my copper solution here, okay, you cannot see the beam going through it. Now it goes through, and you can kind of see it on the, is it going through on the wall over there?
The other one was.
Yeah, there it is on my jacket. I saw it on my jacket. Okay. Anyway, but you can't see it in there. But if I take my colloid now and I shine it through, can you see the beam now going through the liquid?
Not really, but.
Not really?
I think we're supposed to.
Okay, well, watch it this way. Okay, can you see the beam now?
Yeah.
Okay? If I take my salt solution and try to do the same thing, you can see it reflecting off of both sides. Well, you can barely see it going through, okay, because it's probably not totally pure water. But okay, but it's not anything like that.
Wow.
Okay, that's the Tyndall effect. And you say, Mr. Hobbs, who cares about that? Once again, now first off, it's a way to be able to tell the difference between a solution and a colloid. With a solution, you don't get the Tyndall effect. With a colloid, you do. Okay? But y'all are all learning how to drive, or you're just now getting your driver's license. Hopefully, but if you get your license, you already know how to drive. Okay? But when you're driving at night and you're on a country road, you can see your headlights, the beams. Or let's even just go practical. You go to the beach and you have a flashlight and you go looking at crabs at night, okay? And you shine the beam up, you can see the beam of light into the sky. Everybody know what I'm talking about? You see the beam. That's the Tyndall effect. It's because there's little tiny dust particles all in the air that it causes the light to scatter. The particles are big enough, the light bounces off of you, scatters, you can see the beam. But if you go to drive on a country road on a rainy night, what does the rain do to all that dust? I see sign language in the back, and there come from Kate. It washes all that dust out of the air. Then we get just a solution of nitrogen, oxygen, carbon dioxide, and all the different things. Now there's no dust particles in the air. They're all getting washed out by the rain, so there's nothing to scatter the light. So I don't know if you've experienced this or not, but if you're trying to drive at night on a rainy night, you can't see your headlights. It looks like they're not even on. There have been times I've been on a dark road. I've turned my lights off and on just to make sure that they're actually on, because you cannot see the beam. Because we now have a solution. We've gotten all the dust particles washed out. We no longer have a colloid. We now have just a solution, and you don't get the Tyndall effect. You can't see the beam. Now, if we go, and I can take this now, and I'll just go put another piece of filter paper, see if we can just filter this. Okay, everybody remembering how to do that? Fold it in half, grab 3. Okay, and then again I want to wet it to make it stick. So I'm going to take my colloid right here, and I'm going to try and filter it. Oop, aggressively. Okay, so it's coming through, it's clear and clear, but if the particles were too big, then they would be caught by the filter paper. Now again, it's hard for me to know, how can I tell whether or not it's being filtered or not? How can I tell if it's still a colloid or not?
You go through it again?
Shine the light on it and see if we can see the beam. Okay? Now, while we're doing that, oh shoot, do I have enough? Yeah. Okay? We can go to the third one. Okay, well, even while that's filtering, let's do this instead. There are just some examples. Now, you do not need to know all these examples, but these are some examples of what a colloid is. We have a lot of examples of solutions. All soda, all drinks are solutions. Yeah, they have all kinds of color to them, but they don't settle out due to gravity. It's got sugar in it. It's got all kinds of things dissolved. You can't filter them out. They're all just, those are all solutions. Colloids are some of these other kind of crazy things. These are all colloids. It's got medium-sized particles. Notice that some of these, like milk and stuff, they're cloudy, so they're not always clear if the particles are on the bigger side. Okay? Now, let's just see. This is my solution coming through. Can you see the beam going through it?
Not really.
Not really, still?
A little bit.
Trying to get out of some of the light.
Yeah.
Yeah, look from underneath. You look from underneath, okay? You can definitely still see the beam of light, okay? Which tells me, again,
The funnel's in the way. Can't see it.
oh, just poured it all over the table, there we go. It's just, there it is. Okay, so you definitely can see the beam going through the solution, which tells me, oh, I made a mess. Which tells me it's still a colloid. In other words, we could not separate that out, filter. But look at the difference here. What time we get out of here today? 5. Okay. Okay. Solid molecules stay suspended in solution. They will not pass through a semi-permeable membrane. So they're small enough to go through filter, but they won't go through a semi-permeable membrane. Okay, so you got small that goes through everything, medium that goes through the bigger holes of the filter paper, but not the smaller holes of a semi-permeable membrane. Then we have our smallest one, which is a suspension. So if I take some lead nitrate, ooh, that lid was off, I almost did it. Well, I don't want to do that one. If I take some potassium iodide, okay, so we have a solution. But now I take some lead nitrate and mix it with it, okay? Watch it, watch it, watch it, it's gonna be fun. Ooh, ah, ooh, okay? So now, can you see how it's getting cloudy? If it ever gets cloudy, when you mix two things together that are colorless or clear, and then it gets cloudy, that's an indication that, hey, it's no longer a solution. You have a particle, you have something big in there, something that is now, it's a suspension now. It's no longer a colloid or a solution. This is going to be one of our indications that, hey, a chemical reaction took place. We're going to talk about this later on. Okay? Now this will settle out due to gravity. So I'm going to let that just sit for a bit. Okay? I'm going to dump this out. Okay, so a suspension is just your big stuff. That's your muddy water. That's just your big stuff, okay? Now, I'm going to try, let me see if we can see this going through here. It's pretty thick still, okay? But if I come over here, well, let's even do it this way. Watch what's gonna happen when I do this. The whole thing lights up, doesn't it? Okay? The whole thing lights up. You can kind of see the beam in the middle, so a little bit in there, but the whole thing lights up. It's scattering the light completely because it's so big, so many particles. Again, driving tip. What do you do if there's a foggy night with your lights?
Low beams.
Low beams. Because if you put your high beams on, you get the $10 effect on steroids. You get the complete scattering, and all you get is a white sheet in front of you, just like we just saw with this. When the light hits it, it scatters it completely, and you just get light everywhere, and you can't see anything. So you always want to have your low beams on to kind of shoot towards the ground, Because the fog, when you have that much particles, fog is nothing more than a suspension of water droplets in the air. When you have that fog, it just scatters the light completely. So it's really just the Tyndall effect. So you don't want to do that. So now if I take this, okay, you can start seeing it's settling out now. I don't know. Let's see if it gets any better, if we can see it anymore. Can't really. But if I take this and I filter it, I'm gonna put even some more lead nitrate in here just to make it more obvious. Now I need to put this in water, but I'm in a hurry, so I'm just gonna hold it kind of with my finger and then start the filtering. Now notice it's all yellow. But what color is the liquid coming through now?
Clear.
Clear. Because what's happening?
It's filtering.
It's filtering. The yellow is big enough now, the solid, the particles, the solute is big enough to be collected by the filter paper. It can't fit through the little tiny holes of the filter paper anymore. So these are the things that you collect via filtration is only going to be a suspension. Those are the only particles that are big enough that you can filter out. But you can also know that it's a suspension because it's cloudy. All solutions are clear. Okay, not colorless, but clear. Okay? All right, so those are our three types of mixtures. Do you have all the notes filled in?
Wait, so for semi-permeable solution, it can't it does
Okay.
pass through.
Look, here it is right here. This is actually just kind of a summary of all the characteristics. But look, so here's the deal. If we know that you have a filter paper and you have a semi-permeable membrane. Semi-permeable membrane is a finer filter. It's smaller holes than the filter paper. So now we have small, medium, and large. Small goes through both. Medium goes through the bigger hole, the bigger filter paper, the paper, but it won't go through the semi-permeable membrane. The suspension is big, it won't go through any of them. Does that make sense?
Yeah.
Small, medium, large. Two different grades of filters, a bigger hole and a smaller hole. The smallest one goes through both. The medium one only goes through the bigger hole, won't go through the smaller hole. The big one won't go through any of them. And so that gives us kind of the characteristics of our three mixtures. Okay? Solutions are always homogeneous. A suspension is always heterogeneous. And a colloid is medium. The small particles, if it's on the small end of colloid, it'll be homogeneous. If it's on the bigger end of colloid, it's going to be more heterogeneous. But we use the Tyndall effect to determine and separate them all. All right, here's another term for you. Does anybody know what we call the liquid that comes through the filter? This is a precipitate, a solid. What do we call the liquid that comes through? This is going to be in your directions on Monday. Anyone? It's called the filtrate. Filtrate. That's the liquid that comes through. We're going to really learn that on Monday. But when you're filtering something, the filtrate is the liquid that comes through. This is the solid or the precipitate that we're collecting. This is the suspension, the big solute particles. All right? Good deal. Now, so we have mixtures and we have elements. Did everybody get the periodic table that I gave you? So everybody should have a color periodic table. I don't know if anybody was out. You didn't get one? Okay. You didn't get one either? Are you sure?
All right.
Yeah, that. Yeah. Oh wait, I'm looking at it. Okay, so I'll get you one. Okay, I know somebody doesn't have one because I just put them away. They've been sitting up here forever, and you need to ask this. But this is your periodic table of the elements. If it's not on this table, okay, you can shine it up there. If it's not on that table, okay, up all the way to there. Okay, if it's not on the table, then it's not an element. It's got to be on that table. Now your periodic table that I gave to you is way newer than that one. That one was purchased in 2001 when the school first opened. Okay? It doesn't have all of the elements named. Yours is much more current. It was printed, I don't know if they have a print date on it, but it's got almost all 118 known elements on there.
2019, I think.
Okay?
This is revised 2019, so assume 2019.
Revised when, 19?
2019.
2019, okay? But all of these elements here, these are just the Latin names for them on this one because they hadn't been officially named yet in 2001. But since then, they've all been named. The 113, 15, and 17 have been officially discovered, so we're all the way up to 118, okay? Whoever discovers them gets to name them. When the first elements got named, they were kind of named after their characteristics. For instance, chlorine comes from the Greek word chloros, which means greenish yellow, because it's a greenish yellow gas. Matter of fact, it was the first war gas. It was called mustard gas in World War I. You may have heard about that. Okay, but that was chlorine. Bromine comes from the word bromos, which means stench, because it just smells really badly. Let me see. Copper came from cuprum because of the island in Greece where it was discovered. Gold, it comes from the word aurum, A-U-R-U-M, which means shining down because it was a shiny metal. Okay? So most of the symbols, when we look at these symbols, you start with a capital letter, and usually it's phonetic, hydrogen. And then if you have a second or third letter, most of them are only going to have two, but the Latin name said three. But if you had a third letter, the second and third are always lowercase. So I'm going to stereotype here, girls. Sometimes you want to put two capital letters when you do your symbols. Okay, but the second letter always has to be lowercase. Second letter always has to be lowercase. N-A. Okay? So you have, but it's phonetic. Helium is H-E. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. But then we have sodium, Na. And I kind of already alluded to this. Why is sodium Na? Good question. Do what?
Because of what it's made of.
No. Greek or Latin. Okay? Most of them come from their Latin name. Natrium is the Latin name for sodium. Okay, so it's Na. It comes from Latin because they ran out of N's. And then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. And then when you get all the way down here to these, then like thorium, it's named after the Greek god Thor. Protactinium, I'm not sure I don't know if there was a god named that, or maybe he was a geometry guru and he liked protractors. And so protactinium, I don't know where the source of that. But then uranium is named after that planet. Okay? The one nobody likes to say. Okay, whoever named it, I think it's a Roman god or whatever, but you know, anytime you say the planet's name Uranus, you know, you're just going to have to kind of giggle because, and so it was, you aren't old enough, you missed out on this, but the NASA sent out a Voyager spacecraft. It was unmanned, but it was going out and it was going around every planet, little by little. It would circle every planet. It took years and years and years, but it would send back pictures. And so finally it got to around this planet, and the poor little newscaster lady, she would have to go, oh, and here are some exciting pictures of the Voyager out flying around Uranus. You know, there's just no way to make it sound. So they said, oh, we're gonna repronounce it. It's supposed to be pronounced Uranus. That's no better. You know, it's just not a fun. You know, it's an easy one for the junior high boy and me to come out and just laugh and giggle about. Okay.
It's named after the Roman god of death. So
the Roman god of death. Okay.
It's probably why they call it.
Yeah.
Probably bad to laugh at.
Yes, right. I know it probably is bad to laugh at. However, I have to, I should not admit to this. And I believe that this student, God rest his soul, I believe he passed away. But Teddy Spardella, in one of my very first years teaching, I was talking about this, okay? And we were talking about the different planets, and apparently he had been reading a book about the different planets, and he asked me this very serious question. But he said, Mr. Hobbs, why is Uranus green? And I just kind of looked at him and said, Teddy, it's really kind of a personal problem. I really rather not answer. I I felt horrible afterwards. Everybody laughed, you know, whatever. And it's been an indelible moment in my brain ever since. But as I mentor teachers, now, didn't you say 5 after?
I think it's 10:55.
It's 55.
55?
Yeah.
It's 11? It's 11.
Oh.
Okay, it's 11. It's 55? Everybody's for sure. You've been looking on your phones and you
5
know?
minutes of each class.
Okay.
So that means
Okay.
each class it goes down 5.
Okay, so anyway, it's probably a good place for me. Maybe I should cut the video off before that. But as I mentor younger teachers, that's one of the things that I say, maybe you should never say or do, you know, because it kind of embarrassed him. But anyway, it's one of those things that's stuck in my mind is something I probably shouldn't have said in my younger years. Anyway.
We got comedy on the YouTube too.
Yeah. So elements are the simplest form. It's the smallest part of an element. We have our chemical symbols. Some come from Latin. Okay. And then when we come in on Monday, well, actually Monday's going to be the lab. But we'll just talk. We're going to have to memorize these 7 diatomic molecules, diatomic elements. Okay. But kind of go from there. So the key is that it's going to be here. So what's the difference here between CO and CO? Ponder that over the weekend. Go Jags.